In today's video, we're going to cover section 1.2, the definite integral. We're going to cover 5 main topics. So we're going to talk about finding the area under the curve, but here we don't have any restrictions on the function f. We're going to define the definite integral and some of its properties. We're going to talk about the net area. We're going to find the definite integral using some geometry formulas. And lastly, we're going to talk about the average value of function. So let's start with the definite integral. So the definite integral is a generalization for finding the area under a curve. The only difference here from section 1.1 is the function in section 1.1 had to be continuous and it had to be non-negative. When we're finding the integral here, we don't have any restrictions on our function. So the function could be any function defined on a certain interval. Okay, so recall this definition for the area from last time using the Riemann sums. We just took the limit of the summation. So keeping that in mind, we can state our first definition. If we have a function f, like we said, with no restrictions, defined on an interval ab, we can define the definite integral from a to b to be the limit of the summation, which is the Riemann sum. Now, since we're assuming that this limit exists, it means that my function is integrable. Okay, so definite integrals represents the area under the curve. So keep that in mind. Whenever you see an integral, it defines an area under that curve. So let's start with the notations. The general notation for any definite integral, we have the integration sign, we have limits of integrations. Sometimes I'll call them my bounds, upper and lower bound. The function that's inside of your integral is called the integrand, and dx, or d to any variable, this is the variable of integration. Like I said, a is the lower limit, b is the upper limit, and they're both x values here. Now the variable of integration, which is like my x here, it's called the dummy variable because I can write any variable that I want and it's not going to impact my integral. So for example, if I have like f of x, d of x, it's going to be the same if I write it in terms of u, it's going to be the same in terms of t or any different variable. Okay, so let's remember this fact. Last time we said that if f is continuous on the interval ab, this limit is going to exist and be unique. And since we defined the integral to be equal to this, it means that if my f is continuous, then my f is going to be integrable. Now keep in mind that I could have discontinuous functions and they could still be integrable. Okay, so this is the definition for the definite integral. Now I want you to keep the fact that definite integrals are numbers in the end, because once you evaluate them, you're going to get a number in the end. Indefinite integrals that we're going to cover in future videos might not be numbers. They're going to be like functions. Okay, so now let's start this example here. If I want to evaluate this integral from 0 to 4, x cubed dx, and I want to evaluate it using the right endpoints, using the definition that we stated before. So the first thing that we need to do is I want to set up my Riemann sum. To do that, I'm going to find my a. Now a is the lower limit, so it's just 0. b is the upper limit, so it's going to be 4. Now delta x, we already know that the formula for it is b minus a over n. So this is just 4 minus 0 over n. which is 4 over n. Here, since we don't have like a certain amount of n that I want to divide my area into, I just take it n as a general. And then my function is just x cubed, which is my integrand inside of the integral. Now, since we're using right endpoints of the interval, I'm going to find my x of I. Also, using the formula from last video, I have x of I is equal to x of 0 plus I delta x. But x of 0, I know that this is equal to my a, which is just 0. Plus I, and I already calculated delta x to be 4 over n. So every single x of I, which is my right endpoint, is going to be in the form of 4i over n. Now, if you want to plug it into your f of x, this is just x of I cubed. Just substitute the value here. We're going to get 4 cubed I cubed over n cubed. So now the Riemann sum, I know it has this formula, so I'm just going to substitute things in it. So this is the summation from I equals 1 to n. 4 cubed I cubed over n cubed multiplied by 4 over n. Now, since this integral, since this summation only depends on I, so I'm only switching my I values, I can take everything else out. So I'm going to have 4 to the 4th over n to the 4th, summation I cubed, I equals 1, up to n. Now, what do you notice here? I have the summation of I cubed. Also, using one of the formulas or rules from last video, you can easily find it because this is just n squared, n plus 1 squared over 4. This is 4th. Okay, so let's simplify. So this is 4 cubed over n squared times n plus 1 squared. If you expand, just distribute, or if you memorize the formula, you can just find this value here to be expanded to this. And now we can distribute for each one. And we're going to get these terms. Now, since we evaluated the sum here, if I want to find the integral using the definition, I know this is just the limit of the summation. So this is the limit as n goes to infinity for the summation of, we already found it here. So just plug it into your limit. And we know that you can distribute the limit when you have a summation. So these two terms are going to go to 0. And this is constant, so it's just going to be this, which is equal to 64. So this is finding the integral, or the definite integral, using the definition. It's a very long process. Usually we're not going to use it. There's going to be rules and formulas that would be very helpful to calculate the integrals in future videos. But for now, it's good to just know that the integral can be represented as the limit of the Riemann sum. You can easily find the Riemann sum and find the limit and evaluate your integral. Now, the next method that I'm going to talk about is finding the integral using geometric formulas. Since the definite integral represents an area, if I'm able to find an area under the curve with a known formula, I can just use the geometric formula for it and evaluate the area. And that would be equal to your integral. So for example, if I graphed a graph and it was, the area under that graph was a triangle, for example. I know the formula for the area of a triangle. You just evaluate it and find the area, and that would be equal to your integral. So let's do an example so it makes more sense. So let's do number 1. So here we want to use the formula for the area of a circle to evaluate this integral. So let's start by recalling the area of a circle. I'm sure you know that the area of a circle is just pi r squared, where r is your radius. So now if we take y to be everything that's inside of your integral, which is your integrand, so it's going to be equal to this. If you square both sides, we're going to get y squared is equal to 4 minus this. If you move this to the other side, you're going to get x minus 2 squared plus y squared is equal to 4. And if you notice, this is just an equation of a circle. So that's why what's inside of your integral here is just a circle. So this is a circle with radius 2 and and my center is just 2, 0. So if you graph it here, I'm going to graph a semicircle only. This is my center at 2, 0, and this is my radius, which is 2. Now, since I want to evaluate this integral from 0, from 0 to 2, I only care about this area here, which is from 0 to 2. So if you notice, this is only a quarter of a circle. So the area of this shaded part is just a quarter out of the area of a circle, with my radius to be equal to 2. So the integral that I want is just going to be the area of this quarter circle. So it's just going to be 1/4 pi 2 squared. So this is just pi. Okay, now let's look at the second example. I want to find the integral from 1 to 4 for x plus 3 dx. And we want to find this area using the formula of a trapezoid. So let's start by reviewing the area of a trapezoid. So the area is just a plus b times h over 2, where a and b are my bases, and h is just my height. So once you graph x plus 3, you're going to get this line in black. And we're integrating from 1 to 4. So this is the only part that I care about, just from 1 to 4. And if you can see, this is my a, this is my b, and this is your height. Now, finding the height is very easy because it's just the difference between 1 and 4. So the height is just 4 minus 1, which is 3. Now, how about my a? Now, since this a is a y distance, when x is equal to 1, your a is just going to be f of 1. Similarly for b, since it's a y distance, when x is 4, your b is just f of 4. And our function here is just x plus 3, which is my integrand. So we're just going to substitute. So f of 1 is just 4. F of 4 is just 7. Which means that the integral from 1 to 4 of x plus 3 dx is just going to be the area of a trapezoid, which is 4 plus 7 multiplied by your height 3 divided by 2. So this is just 33 over 2. So that's the area under this curve from 1 to 4, which represents my definite integral from 1 to 4. Okay, so far, we either find the integral using the definition, or if I'm able to find the shape with a known formula, I just find it using a geometric formula for the area under the curve of that known shape. Okay, so let's move on and start talking about the net signed area. So let's assume that we're taking this function, 2 minus 2x squared, on an interval from 0 to 2, and we're going to divide it into 8. So my n is 8. And here I'm going to use a left endpoint approximation. We know that if I want to use a left endpoint approximation, we're just finding the area for different rectangles with a constant width and a certain height. We know that each rectangle has this area, which is f of xi star times dx. Now the problem is, when you look at this graph, since I don't have any restrictions, it could be non-negative. So I have like a part of my graph that's under the x-axis, which means it's kind of negative there. So any f of xi here is going to be positive, since it's above the x-axis, which means that the area, which is my f of x times delta x, is just going to be the area of a rectangle, which is positive, like we did before. But what happens if I find f of xi star here? Since this part of the graph is below the x-axis, my f of x is going to be negative. So here we're getting an area of a rectangle, but it's going to be a negative. So these rectangles are going to be positive areas, while these rectangles are going to be negative areas. So the Riemann sum, which is like summing up all of the areas of a rectangle, is just going to be the area of the rectangles above the x-axis, which is positive, minus the area of the rectangles below the x-axis, since we're going to get negative areas below the x-axis. So now if we apply the definition with taking n goes to infinity, my integral from 0 to 2 for the function 2 minus 2x squared is just going to be the limit of the sum, like we stated before from the definition. But this is going to be equal to the area under the curve in the positive part, which is above the x-axis, subtracted from the area below the x-axis. So we're going to call all areas that are above the x-axis to be A1, all areas below the x-axis to be A2. So to find the overall area, or the net signed area, it's going to be A1 minus A2. So the net signed area is just A1 minus A2. And this is going to be equal to your integral. So to find the integral where you have positive parts and negative parts, you just subtract these two parts. Okay, so some facts here. The net signed area could be positive, negative, or 0. It's going to be positive when the area above the x-axis is going to be bigger than the area below. It's going to be negative when the area below the x-axis is going to be larger than the area above the x-axis. And obviously it's going to be 0 when they're equal, because if you subtract the same amount, it's just 0. So let's do an example and understand it a bit better. If we want to find the net signed area between this function, x minus 3, and the x-axis on the interval from 0 to 6. Okay, so we know that the net signed area is just A1 minus A2, where A1 is the area above the x-axis, A2 is just the area below the x-axis. So this is my graph. This line here is just going to be my x minus 3, which is my f of x. And since we're doing the interval from 0 to 6, I'm going to have these two areas. One area above the x-axis and one area below the x-axis. The area above, it's called A1. The area below, it's called A2. Now, how would we find them? If you notice here, both A1 and A2 are triangles. So using a geometric formula for the area of a triangle, we know if I have a triangle, the area is just 1/2 times the base times the height. So we can easily find it from the graph. I'll just find the base and height from the graph and apply it in the formula. Okay, so A1 here, it's going to be 1/2. But what's my base and what's my height? The base here is going to be 3, right? Because 6 minus 3, that's just 3. And then the height, again, this is the height of the triangle, which is my y value when x is equal to 6. If you plug in 6 into your f of x, this is just 6 minus 3, so this is just 3, which means my A1 is just 9/2. Now, similarly, if I'm finding the area of A2, this is just 1/2 times some base and some height. If you look here, the base is just 3 because the distance from 0 to 3 is just 3. And then my height is this here, which is my y value when x is equal to 0. If you plug in 0 here, you're going to get 3, -3. But since we're dealing with distances, I'm going to take the positive of it. So it's just going to be 3. So the area for A2 is also 9/2. So if I want to find the net signed area, we're just going to subtract A1 minus A2. So the integral from 0 to 6 of my function is going to be my net signed area, which is A1 minus A2. So it's just 9/2 minus 9/2, and it's just 0. Okay, so an application of the definite integral, we can have v of t, which is my velocity for some object, depending on some time t. The area under the curve will tell me how far the object is from the original position, or you can call it the distance of the distance that my object traveled. So the area under my velocity function is going to be my distance, and I can find the area under my velocity function using the integral. Okay, so let's do an example. If a car traveled north from a starting position in a straight line, speed 90 miles per hour for 2 hours, and I want to find how far did the car travel. Since I'm doing how far did the car travel, I want to find my distance or my position, and I know that the area under the velocity function is my distance, and an area is an integral. So I'm just going to find the integral from 0 to 2. So 0 is my starting point, and 2 is, since I'm finding at the position after 2 hours. And here, since the velocity is constant, my function is just 90. And I'm integrating in terms of t because I'm dealing with time. So here, this is my function. It's just a straight line, 90. And I want to find it from 0 up to 2. So the area under the curve is going to be this rectangle. But I know that the area of a rectangle is just width times height. So this is just going to be 2 times 90, which is 180. So the car traveled 180 miles. Now let's take the same car, but let it travel south at a speed of 40 miles per hour for 3 hours. And I want to find the final position of my car. Here, I'm going to use the net signed area because it's going to allow me to take the direction into account. because I can take a negative direction. So here, repeating the same process, this is the same thing as above. Now the second part is I'm taking the car that traveled 40 miles per hour, but it's traveling in the opposite direction. It's traveling south. So that's why my function is going to be negative 40. And I'm taking it after 2 hours, and it's traveled 3 hours. So I'm going to stop at 5. So the area here is also an area of a rectangle, but it's going to be negative. So to find the overall position, I'm integrating the first part, then I'm adding the integration of the second part, which is my net signed area, because I'm taking area above the x-axis, area below the x-axis, which is just A1 minus A2. Now A1 is just, like we said before, 2 times 90, so it's 180. But A2 here, let's see, my width is 3, right? Because 5 minus 2, this is my distance here, so that's 3. And then my height here is going to be 40, since we can't have negative height. So it's 120. So the net signed area, or the overall position in the end, it's going to be 180 minus 120, and that's just 60. Okay, so the question here, what if I want to find the total distance traveled, not the final position? What we do is just, I'm going to add up the distances in both directions, but it's going to be positive, right? Because I want to find the total distance. So the total distance is just going to be these two areas added up. So it's just 180 plus 120, which is 300. So if we want to find the area between the curve and the x-axis, regardless whether it's above or below the x-axis, we just add the values up without the negative. And this is what we call the total area of the graph. So we have this definition that summarizes everything. If we have a certain function defined on an interval AB, and we have A1 to be my area above the x-axis, A2 area below the x-axis, the net signed area is just going to be the integral, which is A1 minus A2. But the total area, we're going to take the absolute value of my function, because I don't want to take anything negative. And if I want to represent it in terms of A1 and A2, it's going to be the sum of A1 and A2. So if we go back to this example that we did before, where we calculated the net signed area, I can easily find the total area by just adding A1 plus A2. So instead of subtracting like we did for the net signed area, we're just going to add. So it's just 9 over 2 plus 9 over 2, and that's just 9. Okay, let's move on into the properties of definite integrals. These are the main properties that are going to be very, very helpful during solutions. So let's start with the first one. If I'm integrating from the same bounds, so my lower limit is equal to my upper limit, my integral is just going to be 0. Because if you think about it, an integral is an area under a curve for a certain distance, from A to B, for example. But here, if I don't have like any distance, it's just a point. And the area under a point is just 0. I don't have an area. Also here, if I'm integrating from B to A, you can take it as a negative and just switch up the position of the bounds. And the third property is where I can distribute the integral if I have a summation or a subtraction into two separate integrals. If I have a constant inside of my integral, I can just easily take it out. And if I have an integral from A to B, I have a value C between A and B, I can just split the integral into two parts. exactly like we did for the summation in the previous video. We also have a comparison theorem. So if my function is positive, it means that my integral is also positive. If I have a function that's bigger than another one, so if f is bigger than g on a certain interval, the integral of f is also going to be bigger than the integral of g on that interval. And now, if I have two constants, m and b, m and capital M, if my function is between them on the interval a, b, using property 2, I can apply it here twice. So the integrals are also going to be in that order. And if you evaluate it by graphing the line m, it's just going to be m times b minus a, and your integral is between these two values. Just keep that in mind. Once we do solution, it's going to make more sense once we do that. Okay, so let's do an example so we can apply what we've learned about the properties. So if I have the integral from 0 to 6 to be 4, the integral from 0 to negative 4 is 10, and I want to find the value of the integral from negative 4 to 6. So here, let's start. I want you to think about the property where I can split my integral. Now, I can easily split it with any point between negative 4 and 6. But we want to be smart here. I want to choose a point between negative 4 and 6 that's going to help me find the general integral. Using the facts, using these two facts, you'll notice that I have a 0 here. So it only makes sense that I'm going to split my integral with a 0. Okay, perfect. Now, this integral, I know that it's equal to 4 directly. But how about this integral here? The integral from negative 4 to 0 is, I don't have it directly. I have the integral from 0 to negative 4. So here I'm going to use the property where I can flip the bounds by taking a negative sign and just flipping them. And now I have all information needed to just evaluate it. This is just going to be negative 10 plus 4, which is negative 6. And you can use all of these different properties to split integrals, combine them into one, depending on the question. Okay, for the second example, I have a function f, which is equal to 2x plus 1, a function g that's equal to x squared, on an interval 0 to 1. And I want to compare these functions. So let's look at the graphs here. If you graph your function f, it's going to look like this. That's my line. And if you graph g, it's just going to be x squared, which is the regular graph of x squared. And I want to compare my function f and g on the interval from 0 to 1 here. So if you notice, from 0 to 1, my function f is above my function g. So when a function is above the other one, it means that f of x is bigger than or equal sometimes than g of x on 0 to 1. If you look at this part here, if we take a different interval, let's say like a negative interval, you can notice that g is bigger than f here. So keep that in mind. If a function is above the other function, it means it has bigger values on that certain interval. Okay, so now since f is bigger than g on 0 to 1, I can also state that the integral from 0 to 1 of f of x is bigger than the integral from 0 to 1 of g of x, which means that the area under the curve of f is bigger than the area under the curve of g on the interval from 0 to 1. So yeah, these are comparisons that could be helpful in solutions in future videos and sections. And the last topic that we're going to cover today is the average value of a function. If my function is continuous on an interval a,b, I can find the average of the function on that interval easily by taking this fraction, which is 1 over b minus a, multiplied by the integral of f of x from a to b. There's a proof for this formula in the book. You can read it through. If you have any questions about it, you can email me and I will explain it. It's not that important, but if you're interested, you can just read it from the book in section 1.2. Let's do a quick example on finding the average of a function. So if I take my function to be x plus 1 on an interval from 0 to 5, and I just want to find the average value. The first step, obviously, is just finding the integral from 0 to 5 of my function. To find an integral, I can easily just graph my function. So this line is just x plus 1. And I'm taking it from 0 to 5. So this is going to be my area under the curve that I want to find, which is an area of a trapezoid. So we just want to find A, B, and H, which is my two bases and the height. Similarly, like we did before, A is just f of 0. If you substitute it into x plus 1, this is just 1. B is your f of 5, which is just 6. And then your height is the distance between 0 and 5, so that's just 5 minus 0, which is 5. If you plug it back into the formula of the area, this is 1 plus 6 multiplied by 5 divided by 2. So that's just 35 over 2. But we want to find the average value function, so the average value function is just 1 over b minus a, the integral from a to b of your function. My b is 5 minus 0. And this integral is just my area, basically. So this is 1 over 5. So let me just write it. This whole thing is equal to your area, because an integral is just an area under a graph. So I already know that my a is 35 over 2. So this is just 7 over 2. So these are basically my main ideas. There are more examples in the book that you can read through. You can do some exercises just to make sure that you understand everything. If you have any questions, please just email and we can talk about it. I'll explain more if you want. And yeah, if you go to homework 1, you can do these problems. I'll post these notes on Brightspace too, so you'll have them if you want to read them and everything. And obviously the book is a very good resource that you can use and read through. Let me know if you have any questions or if you want to talk about anything, and good luck with everything.